Today I would like to invite you to some brief journey about on stability analysis through the Koopman operator. So it's somehow a summary of 10 years of research, and this actually started with some pioneering work of Umesh, who studied stability, but with the dual framework of the Koopman operator, so more the Perron-Frobenius operator, but there was already some hint about using Koopman operator for stability theory. And then we started this with Igor in 2014, so 10 years ago, 13 actually, but on the spectral approach. And then I would like to invite you to go all the way through towards the most recent contributions. So first of all, I would like to fix notation, the setting. Here we are considering continuous time systems, and we are considering them on a compact set on Rn. The function, the vector field will be analytic, and we are interested in stability theory, so stability of an equilibrium. So we would like to show that the equilibrium is globally stable on some sets. We would like to estimate the Bayesian of attraction. And this question is of interest in control theory and can also be generalized, in some result can be generalized to other kind of attractors. The flow that is generated by the vector field will be denoted as phi. And regarding the Koopman operator, I recently switched to capital K. So I apologize, not U anymore. Now it's K. And here it's a semi-group of operator because we are in continuous time. We can also define an infinitesimal generator, so we can always define the Lie derivative like this, so it will be the operator A, and if we have some specific strongly continuity property of the generator, of the semigroup, then it's an infinitesimal generator. And we also consider, of course, eigenvalue, eigenfunction that are denoted by phi lambda and the eigenvalue lambda. So this is for the setting and the notation. So let's first talk about the very initial approach, which was the spectral approach. So in fact, it was quite obvious that we could consider the stability properties of a dynamical system through eigenfunctions. In fact, there is a very simple and I would say trivial result that say that if you have some eigenfunctions, phi lambda I, that are just continuous, then you take the zero-level set of these eigenfunctions, you take the intersection, and this intersection will be globally stable over the support of the eigenfunction. This is really easy to prove. So it was the first result showing that, in fact, we have a theory that can mimic the linear theory, where indeed, if we have a linear dynamical system, we can study stability through the spectral properties. Here we can also do this for a nonlinear system through the spectral properties of the Koopman operator. And in fact, we can also directly get a Lyapunov function from the eigenfunction. So here we are in, let's say, in 2 dimensions. We have 2 principal eigenfunctions. We can combine them this way, for instance. It's not a unique way. And it's very easy to prove that we'll have a decreasing of the eigenfunction, of the Lyapunov function along the trajectory. And so we did this 10 years ago, more or less, but after that there was some following works using, for instance, deep learning or machine learning in general, just to find the best eigenfunction to get the best Lyapunov function for the dynamics. But there is an issue, is that the fact that this eigenfunction, we can only compute it approximately. So the Lyapunov function that we get here is not an exact one, it's just a candidate Lyapunov function, and we still have to validate it. So this can be done, and one of my students did this recently, using, for instance, a basis of monomial functions. Then you can use SOS, so sum of square type methods, to prove the validity of the Lyapunov function. And for instance, here you have the Bayesian of attraction, the true one in red, and the approximation here in black, when we validate the Lyapunov function in a very rigorous way. Another example here. And if you're interested, there is a toolbox, MATLAB toolbox, that the students developed recently. So this is one way, but there are some drawbacks because you have to compute eigenfunctions. An alternative method, which is quite related, is to use the lift-in dynamics. So in this case, the idea is very simple. As you know, we can use a lift-in and get an approximated lift-in dynamics, which is linear now, and then we can use usual tool from a stability and control theory to get a quadratic Lyapunov function. Typically, we have to solve a Lyapunov type Riccati equation. So we get a quadratic Lyapunov function, but in the lifted state Z. And from this, we can come back to a nonlinear Lyapunov function for the dynamical systems, the nonlinear systems. But again, here the lift-in dynamic, as you know, is just an approximation, unless we are very lucky with very specific polyflow system where we can get an invariant subspace for the Koopman operator. Otherwise, this is just an approximation. And so again, we have to validate the Lyapunov function. This is the tricky part. But because we computed this in this setting, the Lyapunov function, we can still use tools from control theory. So for instance, robust control theory. And for instance, what we can do is consider that we have an error, which is like a perturbation of the linear lift-in dynamics. And if this perturbation, let's say this error, is small enough, then we can show, using some tool from robust control, as I said, that the Lyapunov function is still a valid Lyapunov function. So here I'm not entering into the details. You have the book chapter if you are interested. But it's good, but we could think, oh, maybe we would like to avoid having this approximation here, and we could also try to work directly on the infinite dimensional system, where there is no approximation at all. And so what we can do is first use, so first I would like to make a brief introduction on RKHS, because we'll use it. So maybe most of you already know it, but just in case, so RKHS are Hilbert spaces where evaluation functionals are bounded. So evaluation functional, called here EX, these are functional that will evaluate the value of a function at some specific state point. So EX applied to f will give us f of x. And so these functional should be bounded. So by a Riesz representation theorem, we have a representer function for each of those evaluation functionals, which are these function kx, which are in my reproducing kernel Hilbert space. And from this, I can also define a kernel, which is the inner product between two of those representer functions. And in particular, in our case, we are interested in analytic vector fields, so we'll consider spaces of analytic function, similarly to what Igor showed about Fock space. So here, instead of Fock space, I will consider his little brother, the Hardy space. Okay, so Hardy space is a space of analytic function on the polydisk. So polydisk is the set of complex values in n dimension, such that the modulus of each component is smaller than 1. And the norm on this space is the sum of the square of the Taylor coefficient fk of the function, and the inner product will be just the sum of the multiplication of all the Taylor coefficients. And what is interesting in this space is, and we will use it, is the fact that monomials form an orthonormal basis. Just for your information, the kernel in this case is this form. Okay, so now using this framework, we can somehow reinterpret the lift-in dynamics. Here we will assume that our analytic vector field is in the Hardy space, that all the monomial functions, or at least the some orthonormal basis, when we apply the generator, the Koopman generator on it, it's still in the Hardy space. And we can define the adjoint operator for the generator, but also for the Koopman semigroup. And we'll use some very interesting and useful property, which is the fact that if we consider the adjoint of the semigroup, apply on an evaluation functional, so kx, or the representer of an evaluation functional, we get again an evaluation functional, but at phi t of x. So what we can do is first to, as I said, try to reinterpret the linear lifted dynamics. So z, the lifted state, is just the basis function, so here my orthonormal basis functions, evaluated at x. So it means that it's just an inner product between this kx, this evaluation functional kx, and the different basis functions. So typically, this is just the coordinate of the evaluation functional in the basis. Also, we can rewrite this expression, so pk, so each basis function evaluated along the trajectory. We can use this property, and we end up with this. And so if we consider z dot, we just have to take the derivative with respect to time of this, and then the semi-group is turned into the generator. So we get actually the generator, but the generator of the adjoint. And so in fact, we see that maybe you already know, and I think it's already mentioned in the introduction of our book on Koopman Operator Theory and Control, but this lifted dynamic is somehow the dynamics which is approximated in finite dimension, but for the adjoint of the generator. And so from this, we can go into the infinite dimension and say, okay, instead of the lifted dynamic, I will directly work in infinite dimension on what I call the dual Koopman system. So I consider this infinite dimensional dynamics, but with the dual of the generator. And here I assume I have an orthonormal basis, so it's a separable space. And so instead of considering any function f in my reproducing kernel Hilbert space, I can consider component in the basis. So this component will be this infinite vector z, which is in small L2. And now I have an infinite matrix that I call A bar star, which is the representation in the basis of the adjoint of the Koopman generator. And so my matrix here for the lifting dynamics is just a truncation of this infinite dimensional matrix. And we'll come back to this later. So what can we do with this? But then we can use this infinite dimensional representation for stability. So we'll start from this dual Koopman system. And the hypothesis that we make is first that this infinite dimensional matrix that represents the dual of the Koopman generator is triangular. So all the entries here should be 0. Also, we'll assume that the diagonal entries here have a strictly negative real part. If we can have this, then it's possible to build a Lyapunov function for this infinite dimensional dynamics. And this is this Lyapunov function, which is actually a functional because it acts on each function f in the RKHS. I will skip the details, but the function is simply taking the components of f in the basis to the square, and we have to add some constant, and this is the tricky part. We have to tune properly this constant such that we get a Lyapunov functional that will decrease along the trajectory, but the trajectory in infinite dimension, so through the dual, the adjoint of the Koopman semigroup. So this is the first part, but then we have to come back to the original nonlinear dynamical system, but in finite dimension. Then it's easy. In fact, what we can see is that if we want our Lyapunov function, it's simply evaluated the Lyapunov functional, but at an evaluation functional. So typically, Vx will be this V, but evaluated at Kx. And then you can you do the computation, but it's really easy to see that indeed this Lyapunov function will decrease along the trajectory of the system. So far so good, but there are two issues. So first issue is about this hypothesis. So is it satisfied? And also we have to pay the price for infinite dimension. We got an infinite series, so is it convergent? So does our Lyapunov function exist actually? And we can answer positively these two issues. If we consider an analytic vector field where we have an hyperbolic equilibrium, and if we work with RD space, then the assumptions are satisfied. We will have a triangular form provided that the linearized system, so the Jacobian matrix at the equilibrium, is triangular. And this can be done through just a linear change of coordinates. Also, the diagonal entries will be negative with negative real part because the equilibrium is hyperbolic and stable locally. And the series, we can make it convergence with some radius of convergence. This is possible. And so from this, we can get some systematic criteria for stability just based on the vector on the Taylor coefficient of the vector field. And so we can have some criteria that will tell us from these coefficients, or we are globally stable on this region of attraction for some radius rho. Again, I'm not entering into the detail, but there is a CDC paper, last CDC paper on this topic. Okay, so I'm already getting to the end, so I try to catch the time. So now we would like to go more toward the data-driven approach, and this is still ongoing work, I would say. So the idea is that instead of having the knowledge of the vector field, we would like to infer stability about the dynamical systems from the data. And this has been started recently, also a CDC paper last year, but using just standard EDMD, so using discrete L2 projection, just to get an approximation of the Koopman operator. A tricky part is validation, but I'm not entering into this detail. But instead of this, we would like to use another approximation, and we would like to come back to this idea of truncating the Koopman matrix, which is somehow useful because we have seen that it has a triangular form. And we would like to preserve the triangular form because we have seen that we can use it for stability. And what we can, and this triangular form also is very important because it preserves somehow the spectral properties. So when we truncate the matrix, if we preserve the triangular form, then the eigenvalue that we get are actually the exact eigenvalues. And the eigenfunctions that we get are just the projection of the true eigenfunctions. So it's still quite useful because with standard EDMD, the eigenfunctions that we get are not really the projection of the true eigenfunctions. And so somehow we are inspired by Julia's work, where we can think of this truncation just as a projection, an orthonormal projection here on monomials, because monomials form an orthonormal basis. So if we pick the right space of function, considering an orthonormal projection will just be a truncation. This is really what we want to do. And I forgot to say that we also know that this kind of projection, when we know the vector field, is a good way to get a nice approximation of the basin of attraction. So can we do this from data? And I mean from real data. Real in the sense, not complex data. And this is possible. So Igor has already showed a bit, but maybe I will enter just a bit more into the detail, but not that much because time flies. So we have data matrix X and Y as usual with EDMD. And we can consider then a kernel matrix related to the kernel either of the RD space or some Taylor type kernel that is associated to RKHS where we have orthonormal monomials. So typically it could be a Fock space, for instance, or the exponential kernel. And so this projection, so where we take the finite truncation, so orthogonal projection in this space on monomial is simply given by the multiplication of these two matrices. And so we multiply by Y and we get a new approximation, which is quite simple actually. And then we have these result. Igor already showed this picture. So here it's for the van der Pol dynamics, but the one where the equilibrium is stable. So the limit cycle is unstable. So we can get very good approximation of the eigenvalues with this nice lattice of eigenvalues until order 7, I think. So at 8 now it's not going well, but till 7 is fine. And we have the approximation of the Taylor coefficient of the eigenfunctions to order 8, just using 250 data points. And so the next step will be to use this for stability analysis, data-driven stability analysis, but this method is not limited to stability analysis. We could use it for identification, network, spectral network identification, control, of course, and so on. So with that, I haven't really prepared a nice conclusion, so I hope you enjoy this brief journey of 10 years of research in stability theory, but I should at least acknowledge my collaborator. So Igor was very involved all the way through in this topic, but I also work with Eivar Soutla and my 2 students, François-Grégoire Berroir and Christian Mugisho Zagabe. So I thank you very much for your attention.